ます。はい、じゃあ、let's start today's class. This is the third class of Bioengineering. Yes, this is a story up to here. Partly I have mentioned about the brief introduction about the structure and functional feature of biological bodies. And then last week we have discussed about the bioengineering field, one of the bioengineering field, what it is we have discussed. And then from today, these 2 weeks, we will focus on the sensory information system. Yes, sensor, nerve system. This is the one interesting point maybe you. So therefore I pick up this sensory organs firstly, sense. Characteristics of sense and sensory organs. And then the second part is skin sensation. Okay? Especially in the skin sensation. So start with the general definition about sensory organ. What is sensory organ? How do you think about the definition of sensory organ? ここに書いてありますけど、sensory organ は one of the transducer, transform some various physical or chemical information received, and then it transfer into the signal, especially neural pulse signal, some action potential, voltage. This is the sensory organ is a transducer, some physical chemical information transferred into the voltage signals. This is the definition. And the sensory organ is separated in especially in the receiver's part, receptor. It is called receptor. Some physical chemical information received part is a receptor. And sensory organ is not only receptor but also other the primary signal processing part is included. And then the complicated sensory system, sensory devices is called sensory organ. And then you may know this is 1, 2, 3, 4, 5 senses. Yes. This is 5 major senses in human beings. What it is? Eye. Vision. Visual sense. Ear, auditory sense. Auditory. Yes? Sound. Hand は何かな? Tactile sense ね。Tactile sensation. Tactile sense. これ nose はスメルなんだけど olfactory sense. Olfactory sense. であれは tongue だけど taste sense. ね。Taste. Do you think what is what 5 senses is categorized into 3? What it is? 5 senses is categorized into 3. One categorization is maybe you know one categorization is the remote sense and tactile sense という categorization. One, the remotely sensing or the touching sensing or contact sensing. This is one categorization method. For example, visual and auditory is a remote sensor, and this is tactile sense. You may know. And then another categorization, what it is, 3 category. There is 3 category, what it is. Another categorization method. This is categorized into 3 parts. What it is? Time to think.
Country and mechanical and light.
メカニカルでね、タクタイルはね、メカニカルです。メカニカルでね。あと、なんだ、オーディトリーもなんかメカニカルでね、ウェーブだから。プレッシャー、エアプレッシャーだからね。This is mechanical information でしょ。このタクタイルのメカニカルインフォメーションですね。これはオプティカルですね。オプティカルインフォメーション、リシービング。で、ノーズやテイストはケミカルだよね。ということで、ここはメカニカル、ケミカル、オプティカル。で、それは次のページにここに書いてあるんだけど、オーディトリーとタクタイルはメカニカルセンセーションだし、ビジュアルはオプティカルセンセーションだし、テイスト、オルファクトリーはケミカルセンセーションだよ。ね、まあ、この5 senses is also categorized into another categorization method. And this chart shows the neural system, the neural control information system. So the firstly is a stimulation. Stimulation is given from the outward external world, and receptor, sensory organ, receives the stimulation, and by using the 5 senses, this is the receptor, and then this sensor produces the nerve impulse. This transfer path is called sensory nerve. Sensory from sensor to the brain. Brain means the central nerve system. Central nerve system is the meaning of the brain. From the sensor to the brain, the sensory nerve system is transferred the signals. And then the brain is thinking, and brain make control of the effector organ. Effector organ means some peripherals like arms and legs. And then by using the arm and leg, this living creature makes some effect, the physical effect to the external world. Okay, this circular system is made the sensor controller mode actuator system. It looks like sensing the external world condition, and then the brain is thinking about the processing the information and decide the motion of itself, and then the effector, yes, arm or hand or leg, foot, make some effect to the external world. Yes, this the feedback system, control system is always working. Yes. ということで、the one element is a neuron. This cell, one cell, nerve cell. The nerve cell は consists of the cell body, and from it, this is the axon. Axon is a nerve fiber. In some cases, nerve fiber is more than 30 centimeter or more than 30 centimeter in one cell. And synapse is a connection between the multiple cells, multiple nerve cells. And action potential is the transferred along the axon. This system is given in the next page. It looks like this. This is one cell body, and axon is here, and this is the end of the axon. And this is connected to the next cell body itself. So in this part, this is called synapse. This part is called synapse. Connection area is called synapse. It looks like this. The end of the axon is here, and action potential is, it looks like this. Some pulse is transferred here, and then some material is given to the next cell body, and then this receptor receive this material, and then produce this potential, and then this pulse is transferred to the next cell. So this mechanism is shown like
When an action potential reaches the synaptic terminal of the axon, it encounters a region called a synapse, where two neurons come close together but do not touch one another. A minuscule gap, called the synaptic cleft, separates the synaptic terminal of the first or presynaptic neuron from the dendrite or cell body of the second or postsynaptic neuron. The arrival of an action potential at the synaptic terminal causes the synaptic terminal to become positively charged and release neurotransmitters into the synaptic cleft. The neurotransmitters diffuse rapidly across the synaptic cleft and bind to receptors in the membrane of the dendrites or cell body of the postsynaptic cell. Each type of receptor in the postsynaptic membrane binds to a specific type of neurotransmitter, and after binding to a neurotransmitter, the receptor causes specific types of ion channels in the postsynaptic membrane to open. As ion channels are open, ions flow across the cell membrane of the postsynaptic neuron along their concentration gradients. This flow of ions into the postsynaptic neuron causes a postsynaptic potential in the dendrites or cell body. Depending on the channels open and the ions that flow in, synaptic potentials can be either excitatory, making a neuron less negative inside and more likely to fire an action potential, or inhibitory, making it more negative and less likely to fire. An excitatory postsynaptic potential is called an EPSP. An inhibitory postsynaptic potential is called an IPSP. A synapse that produces EPSPs in the postsynaptic cell is called an excitatory synapse, while a synapse producing IPSPs is an inhibitory synapse. Postsynaptic potentials cannot travel far in a neuron. After a few millimeters at most, the ions leak back across the membrane and the signal is lost. However, postsynaptic potentials travel far enough to reach the cell body, where they determine whether or not an action potential will be produced.
まあいいや。もう違うやつありますか？2 minutes neuron science.
Welcome to 2-Minute Neuroscience, where I simplistically explain neuroscience topics in 2 minutes or less. In this installment, I will discuss the neuron. This is a brain. Estimates vary, but right now the best guess seems to be that our brains contain around 85 billion neurons. The neuron is a nerve cell, and it's the primary functional unit of the nervous system. This is a generic image of a neuron. Neurons actually come in all shapes and sizes, but this is the prototypical version of a neuron that you'll often see in a textbook. The structures extending from the left side of the neuron that look a little bit like tree branches are called dendrites. Dendrites are the area where neurons receive most of their information. There are receptors on dendrites that are designed to pick up signals from other neurons that come in the form of chemicals called neurotransmitters. Those signals picked up by dendrites cause electrical changes in a neuron that are interpreted in an area called the soma, or the cell body. The soma contains the nucleus, which contains the DNA, or genetic material of the cell. The soma takes all the information from the dendrites and puts it together in an area called the axon hillock. If the signal coming from the dendrites is strong enough, then a signal is sent to the next part of the neuron, which is called the axon. At this this point, the signal is called an action potential. The action potential travels down the axon, which is covered with myelin, an insulatory material that helps to prevent the signal from degrading. The last step for the action potential is the axon terminals, also known as synaptic buttons. When the signal reaches the axon terminals, it can cause the release of neurotransmitter. These purple structures represent the dendrites of another neuron. When a neurotransmitter is released from axon terminals, it interacts with receptors on the dendrites of the next neuron, and then the process repeats with the next neuron.
ということで、connection of the neurons is transfer the information to the brain, to the sensor to the brain, and the brain to the other peripheral arm and legs and the other part. Yes, and then the next is sensation features, human sense characteristics. Its vision is minimum for joule って書いてあるけど、the dynamic range is 10 and 9 times, and hearing is auditory senses looks like this, and the vibration senses looks like this. So therefore, maybe you can find a very large, wide range of dynamics. Wide dynamic range can be captured by sensations. But the level of distinguish, it means which kind of discrimination level this vision system can catch, or hearing system can catch, and vibration system can catch. So it says about the vibration, only 15 steps we can distinguish. But the hearing, the auditory senses, the very, very small sound, and to white and the big sound we can catch. And it can distinguish of the 300 levels. We can discriminate 300 levels. But more about the vision system, we can find the very, very dark condition to the more slightly bright and bright and more bright and bright condition. So we can distinguish 600 steps. So therefore, the vision sensation is very, very strong sensation for the human being, human senses. Okay. High sensitivity. High sensitivity means I will explain later, but high sensitivity and wide dynamic range is human sense, especially vision and hearing. And how about the rate of information throughput? Looks like this. The vision system is, it codes about 3 bits per second. Hearing system is 2 and 7 bits per second, it says. And nose and smells looks like this. So therefore, not so fast about the transfer speed. I don't know, but that is fact-based. Fact-based. This table shows, but some table says looks like this. ジュールとかなんかモールとか書いてあるんですけど、ガルこれか。ガルはアクセラレーションですね。ビットはビットですね。インフォメーションユニット。And the classification of sensation is looks like this: spatial sensation, the somatic sensation, visceral sensation. This looks like this. For example, some special organ is there, or skin sensation, or deep the inside body sensation, or the more deep inside body sensation, and so on. It is where it happens. Looks like this. And then this is mechanical stimulus, the optical stimulus, thermal stimulus, chemical stimulus. So the sensation looks like this, and the sensory organ looks like this, and the receptor cell looks like this. This is only the table, so the not so much important of the specific words. maybe this is more important, I see. The stimulus, stimuli-led strength for the sensation. Dynamic range. What is a dynamic range? As I used the without definition, but the dynamic range is one sensory organ can capture the stimulation. This range is called dynamic range. From the some small amount of stimulus and the large amount of stimulus, it works. Works means by receiving some stimuli, some output signal generated, it means. So the range of working is called dynamic range. And then the absolute threshold means the minimum stimuli, minimum magnitude, minimum strength of the stimuli when producing some output signal. Yes, absolute threshold is a minimum threshold of stimuli, minimum amount of strength of the stimuli to produce the output signal. This inverse number is called sensitivity. When the absolute threshold is smaller, the sensitivity becomes higher. Yes, the very small amount of stimuli it can react, and so therefore the sensitivity becomes high. Absolute threshold becomes low, the sensitivity becomes high. This is inverse number of absolute threshold. Yes. But this is called this is only about the stimulus magnitude of stimuli. Small amount of magnitude で this sensor can produce some output signal. So this is the threshold, absolute threshold. And if this absolute threshold is the amount of threshold is become smaller, it means the sensitivity is become high for this sensor. But another word has a discrimination threshold, differential threshold. Yes, some amount of signal is a stimuli is given to this sensor, and it can produce some signal output signal. But how about a little bit larger stimuli is given to here? This is also some amount of signal is produced. But how about the difference between these two signals? Yes, this one signal, this is second signal. This is a difference or not? Yes, this is only the slight changes is here. And how about this output signal is different, is or almost the same or not? It is the discrimination threshold. Yes, the reference signal is looks like this blue line, and some slightly different signal, this red line is given. And how about the output? This is become different, or this is almost the same. So the output, input stimulus the strength is a small minimum amount of difference. It's make this difference, output signal the difference. This is called the discrimination threshold. Yes, the next page. So therefore you can estimate this Weber-Pfeffiner's law. Weber-Pfeffiner's law. Weber, Ernst Heinrich Weber and Gustav Theodor Pfeffiner, both are German psychologists. They are working in the 19th century. Yes, this graph, this chart shows that this horizontal axis shows the amount of stimulus. Amount of stimulus is looks like this, and the vertical axis shows the output signal. Output signal, né? So in this chart shows some chemical material given. Chemical materials density is given to here, and this is output signal. In this case is smell. Né? This is very bad smell. Bad material is here, and the output signal looks like this. So maybe you can easily estimate there's nothing condition and slightly smell. You can react so rapidly and sensitivity. Another double the amount of smells is here, and you can find this is here and this is here. You can smell more smell, bad smell you can catch. But from here, this smell looks like this. You can feel the bad smell, but almost the same amount of density is increased. But your sensitivity is your smell sensitivity is look like the same, almost the same, not so much changed. So therefore, in lower levels, your smell sensitivity is very high, but higher sensitivities, higher densities, your sensitivity about the smell is looks like the lower. It is very easily you can estimate based on your experience. これウェイバーズローってちょっとなんか見てみますかこれ。
So, this brings us to something called Weber's law. So Weber constant proportion in order for their difference to be perceived. So in English, if we're starting with paper or if we're moving to a textbook, it kind of doesn't matter because you're going to need a certain proportion of difference for that to be detected. Okay, so that delta is difference threshold, or the JND. And it kind of depends on the medium as well. So weight versus light versus sound, you're going to have differences, but the proportion within each medium is consistent. Okay, so if you're starting with 5 pounds and I change that to 5.01 pounds, you're probably not going to notice that difference. But if I go from 5 pounds to 5.5 pounds, you might notice that. Now, if you move to, say, light, and we're looking at lumens of light, you need a certain difference there, and that proportion is going to be different than what you see for weight, and the same thing holds true for sound. So we can look at these by certain senses, and this is an average and a generalization, so it can vary as well. But in weight, you need roughly a 2% JND. In light, roughly 8% JND, and for sound, or roughly 3% change for you to detect that difference. So this is a equation that is for sure going to show up on the MCAT, so we should know this, and this is Weber's law. We're going to walk through the 3 components. So delta I represents the difference threshold, so the JND. This means the difference from your stimulus. And the I represents the initial stimulus intensity. So what were you starting with? The delta is the difference, and you put those over one another, you're going to get the K, which is Weber's constant. Okay? Now, let's go through an example. And this is an MCAT style question that's probably going to pop up, and we're going to present a passage or a scenario, and you're going to pull out bits of information.
まあなんかこう例を言ってるけど、だから例えば なんかウェイトの時に5ポンド5キログラムでプラス 0.5 グラムというのと1グラムプラス 0.5 very different sensation you feel. The very small amount, it is a basement is a very small, this is basement is very large, and the difference is the same. So therefore you feel more sensitive, but you may not feel so much. The brightness is also same. Some look luminous or some looks the brightness condition, and more some light is added, or dark condition and the some light is added. You feel more sensitive at the dark condition with the same light. But the bright, yes, in the daily light and the night condition, you feel the different. This is the same. Okay? まあこういうことですね。でこれは very なんか you are experience based. You can agree easily. But this is only some cases. The waiver technique's acceptable scope is very narrow and limited. Visual sense, auditory sense, and also the medium amount of amplitude of the stimuli. So therefore, more wide range and more other sensations. The sensation intensity rate of change will depending to the stimuli strength. This graph is produced by Stevens. Stanley Smith Stevens, American psychologist, shows this graph. This is relatively strength. This is これは10 to 10, 2 times, 3 times, 4 times, 5 times とかなっていて、でこれはpressure. So this is some sensation is some stimuli is given to the participants, and then the grip dynamometer's gripping force, the participant reply to the sensation amplitude, amount of sensation. This is white light, and some noise, and some pure noise, and vibration, noise, and some amount of stimuli is given to that, and the grasping force is the response by the participant. So it is along this line. So therefore, this equation is matched to very wide range and very variety of stimuli. The Stanley Smith Stevens has find out that.
Stanley Smith Stevens was an American psychologist who founded Harvard's Psychoacoustic Laboratory, studying psychoacoustics, and he is credited with the introduction of Stevens' power law. Stevens authored a milestone textbook, the 1400-plus page Handbook of Experimental Psychology. He was also one of the founding organizers of the Psychonomic Society. In 1946, he introduced a theory of levels of measurement widely used by scientists but criticized by statisticians.
いやというようなことでいいですね。はい。ということですが、これがまあ一つのbasics about the strength ね、amplitude, strength の some law. But the time change about sensation, you may feel adaptation. Some stimuli is given, but the sensation is adapted to that sensation, that stimuli. So therefore, the output signal will become reduced and sometimes fade out. ね、それはレセプターセル。まあ、one of the adaptation is it happened at the receptor cell itself, the sensor itself, and other adaptation is happened at the sensory nerve fiber system, sensory nerve systems. ね、でレセプターの起きるやつと、ナーブファイバーで happens。まあそれがあるよ。で例えばフォトアダプテーションはナーブファイバー。It happens at the nerve fiber。でライトアダプテーション、ダークアダプテーション、it happens。But the receptor cells, for example, tactile sensations adaptation is happened as the tactile sense at the hand itself. まあこういうやつですね。ちょっとなんかここも見ますか。一番そうなんです。これか。Sensory Adaptation Definition という。
Sensory adaptation is defined as the diminished sensitivity to a stimulus as a consequence of constant exposure to that stimulus. Brain cells begin to fire when they pick up on a new stimulus in your environment, as signaled by your sensory organs, your ears, eyes, nose, etc. The constant loud sound of a running air conditioner, for instance, seems irritating when it is first turned on. However, within an hour, you'll most likely have forgotten all about that sound and no longer notice it. So if that stimulus remains unchanged in the environment, then the brain cells begin to fire significantly less in response to that stimulus, and the result is a lack of attention to that particular stimulus. There are many instances of sensory adaptation in everyday life, and here we're just going to name a few. In addition to the running air conditioner from the beginning of the lesson, another great example that involves your sense of hearing is the sound of traffic. People who live by busy roads typically don't even notice that there is the sound of constant traffic outside their window. But if someone comes to visit from a more rural area with less traffic, he or she will most likely find the constant sound of traffic irritating. On the other hand, someone who lives out in the country is used to the sound of chirping insects and perhaps other nocturnal animals at night, while someone from the city would hear that and think that was irritating, and maybe even miss the more familiar sound of the city traffic. There is also a large amount of sensory adaptation going on with the sense of smell. People who smoke no longer notice the odor of cigarette smoke, and when people who don't smoke are around them, they wonder how they can stand having their clothes, hair, and pretty much all of their possessions smelling of smoke. Similarly, when people have on strong cologne or perfume, they often don't notice the smell as the day wears on, while other people they encounter throughout the day find the smell of the perfume or cologne overwhelming. The sense of touch on skin receptors works the same way. If you put on a piece of jewelry such as a bracelet, initially you will notice the feel of it on your skin. Within minutes, sensory adaptation comes into play and you no longer notice the feeling of the bracelet on your wrist. However, you can recapture the attention of your skin receptors by moving the bracelet higher up on your wrist, only to have sensory adaptation happen again after a few minutes. Although examples of sensory adaptation abound, there is one sense that is not affected by it, and that's vision. If sensory adaptation did occur with vision, then gradually what you would be viewing would disappear. Since vision is the most important sense for humans, the eye has developed a way to combat sensory adaptation through constant movement. Most people are not consciously aware of the fact that our eyes move constantly, often with slight movements known as saccadic movements. These movements prevent visual sensory adaptation as the eyes are constantly sensing a slightly different view, and therefore nothing in the field of vision remains constant.
これ面白いよね。eye は eye moving, always a little bit moving. So therefore, yes, human sensations, the visual sense is most important, and many information is captured from the visual sense. So therefore, the human organs works visual sense always actively. So therefore, the actively movement is unconsciousness, but to the actively movement of the eyeballs. So therefore, the capturing some slight difference, some slight movement can capture so sensitivity. So it shows. And as a previous topic is also interesting, some urban city living people don't care about the traffic noise. but the countryside people don't care about the insect, bird noises. So therefore the usefulness or usually suffering some noise is very interesting point for these topics.
At first glance, it may seem like sensory adaptation is maladaptive because it draws our attention away from various stimuli. You should note, however, that this only occurs with constant, unchanging stimuli. Therefore, it keeps your brain from being distracted by unimportant aspects of the environment so that you can better focus on what is important. During the time of our hunter-gatherer ancestors, for example, it would be adaptive to not be distracted by the usual sound of insects chirping at night, so that attention could be put to better use by keeping an ear out for lurking predators. Sensory adaptation is the process by which our brain cells become less sensitive to constant stimuli that are picked up by our senses. This process occurs for all the senses except for vision, which is the most important sense for humans. Sensory adaptation of vision is avoided through saccadic movements of the eye. Sensory adaptation is important for daily functioning because it allows our attention to be free to detect new and/or important aspects of our environment without being distracted by aspects of it that are constantly there.
Or new important stimuli you can vividly sense. To do that, some to the eyeball movement, saccade movement is made. Saccade movement でしょ? Yes, so the next is location of sensation. Location of sensation. It is called receptive field. Receptive field. Yes, for example, this is a retina, the eyeball's retina is the visual sensation is the これってだからレティナっていうのはもちろんアイボールアイボールがあってでここにレティナのところになんかこうビジュアルセンスがこうたくさんありますよね。でこの光がでlight is spotted to here and this sense you can catch the center of this it can catch the more vividly. But if its spotlight is given here and given here, this center nerve is produced. Yes, of course. If it just receive this light here, but if some light is given here, this nerve cell can produce some amount of signal. Why it is? It is this is centrally located nerve. Yes, of course, it can produce some output signal when the light is given here. This is look like this. But this cell is also when the spotlight is given to this A area, E area, it can also produce some amount of signal. It can generate. Why it is? まあいいや。Why it is まあいいんだけど。So therefore the one cell's working area is not just this area, but some amount of area it can produce some amount of output signals. That is called the receptive field. Of course, center is the most highest output is given, but not so far from the center position, it produces this amount, and this produces this amount, and this produces this amount. And this area is called receptive field. はい、please は次のページに行ったんだっけ。はい、it is because this nerve cell system has some layer system. Yes, this is a first layer, second layer system, third layer system is here. So the connected each other. So therefore, at this part, this is a end output position is here, output. So therefore, even if this part, some spotlight is given this part, some connection of the layers connection. So therefore, the center part, it produces some amount of signal. わかる？だからこれニューラルネットワークですと This is similar as a neural network. Not only just the center, but also the other part, some amount of signal is produced at the center. これはここの階層間 among the layers, connection and aggregation and divergence is the repeated. The first layer, second layer, third layer. So therefore, not only the center part, but other peripheral parts, some light is given. Some amount of light output signal is generated from the center. というわけです。次。Next is a projection law. This is, I have given some videos before starting this class about this. The phantom sensation, phantom pain, some amount of patient is very severe problem about that kind of problems. Yes, for example, the amputee for the upper limb, from the elbow tip. Someone feels all of the amount of the lost arm is here, or lost hand is here, lost hand is put on here, lost hand is put here. Yeah, some types is there about the phantom sensation, but phantom means the lost limb feels. It is existing still now. So some tactile sensation or pain sensation, he or she feels. The important point is stimuli localization. Yes, brain feels. Yes, for example, without watching this hand, we can feel. Yes, some needle stimuli is given to this hand. I can feel without watching it. So therefore, the localization. This is localization. Only by this feeling, this brain can localize the stimulus position, orientation, and so on. Where it happens. So therefore, the projection means inside the brain, some stimuli given position can be estimated, localized inside the brain. Then one important point is someone watching this video can understand the correspondings. Yes, watching stimuli and feeling stimuli should be corresponding. Yes, I watch it. I was touching this finger to this palm, and this is visual information, and also I feel some tactile information from here. So the visual sense and tactile senses correspondingness inside of the brain is very important. Because any animals, human being, has multiple sensation and visual sensation and also the auditory sensation, hearing, some touching noise is happened here. Yes, auditory sense that can capture this sound. Yes, watching, hearing, and tactile sense. All these stimulus localization is corresponding is very important. So this is important for the human beings' actual daily livings. So therefore, for example, in ちょっと離れるんだけど、なんかロボティックスフィールドだとマスタースレイブってマスタースレイブマニピュレーターとか、あるいはリモートオペレーションってあるよね。リモートオペレーション、ロボットリモートオペレーションね、なんかロボットアームをオペレート、the human being operates some robot using some joystick or some operating devices, and then the slave robot from some part is working here, robot is working to do some task. ね、で、なんか、some, リモートオペレーション is here. でしょ？でも、リモートオペレーションの時は、なんかさ、例えば、using some ちょっとよくわかんない。カメラシステム is watching the environment, and the operator can watch this image to operate. なんか watching some images to doing some. So the feedback information, the visual feedback information is given to him, of course. And also, in addition, the operation to do some tasks by using hand. Maybe the reaction force is very important to an effective work of the achieving task. So therefore, the tactile feedback is also given to this joystick. でしょ？だからなんかさ、ビジュアルフィードバックとタクタイルフィードバックっていうのは given to the operator。ね？でも、but remote operation, fan remote operation、この fan, it is a very long distance. Some time delay is there at the feedback. Time delay is there in the feedback, of course. Some the command is inputted by using the joystick, and the reaction force is given to the given feedback to the operator. There has some the time delay, of course. Time delay. It's okay, the time delay is there, so therefore the act and weight and reaction forces come back. Act and weight and reaction forces come back. It's okay, and the time delay is happened. But more problem is about the visual feedback. What happens? What happens visual feedback? なんでしょう。タイムディレイだけど、だからタクタイルセンスももちろんタイムディレイなんだけど、ビジョンセンスもタイムディレイなんだけど、more problem is happened. What it is? タクタイルセンスって多分フォースとかモーメンタムインフォメーションで some amount of data is necessary to feedback. ビジョンってムービー more amount of information. So the data size is more larger. So more larger means more time delay. So therefore, the tactile sense, visual sense has a different time delay to fed back to the operator. So the operator feels a little bit funny to operate something. That makes the confused about the operating. Okay? So as I said, the localization at the same time is very important. So feedback at the same time, because this remote site, some event is happened at the same time, but the feedback information is given a little bit different time. So it makes confused for the operator. That is the same as sensations. Yes, visual sensation feedback, auditory sensation feedback, tactile sensation feedback must be at the same time, at the same position. Without that, this kind of phantom rib pain or phantom pain has happened. Phantom pain
A phantom limb is just like any other limb that you would feel, except it isn't actually there. Phantom sensations are feeling body parts like arms or hands that aren't on your body. This sounds crazy, and it kind of is, but 60 to 80% of people who have lost a limb report phantom feelings throughout their life, most of which are painful. And almost 100% of people report phantom sensations immediately after having lost a limb. So how does this happen? Well, first we have to understand how we normally feel things. Every body part is connected to specific neurons in the brain. When you detect a physical stimulus, when you're touched, that body part immediately sends a signal to its corresponding neurons in the brain. And when that signal is interpreted by the brain, that's when you actually feel the stimulus. But when you lose a limb, no sensation is given to this part of the brain anymore because there's no limb to be touched. It turns out that when neurons in the brain are really inactive for a long time, the neighboring regions want to expand and fill that void. So what happens next is a sort of reorganization of the brain's neural connections. The active regions that are being touched and stimulated literally start to take over the inactive regions. This process is called neuroplasticity, and until very recently, most people assumed this wasn't possible, that our brains were permanently hardwired and unchangeable. But we now know that the connections are malleable, plastic. Okay, so neighboring neurons have moved into that region, but now what? Let's assume we lost an arm, and the corresponding neurons in the brain eventually become inactive. We know that the neural region closest to this contains the face, so the face's neurons eventually move into the region that before stimulated the arm. This means that whenever certain parts of the face are touched, we would experience that sensation not just in our face, but in our phantom limb too. Here you can see a picture of scientists diagramming where parts of the hand and arm are on someone's face. And similarly, if someone lost only their lower arm, it's likely that the neurons of their upper arm...
いや、ということで、ローアームも同じやりますね。で、次すみません。remaining time is limited, so therefore, yes, the mechanism ね。if you see this bars, this is bright and more darker, little bit darker and dark. How do you feel like this? How do you feel about this? 例えばですね、だから brightness is changed. Yes, bright, little bit dark. It is given like this. ね、なんか bright bar, little bit dark bar, darker bar, darker bar, darker bar ってね。Brightness is changed, but you feel maybe this part is more bright, this part is more dark, this part is more bright, and this part is bright. So you feel that this has some border line is given here. Borderline, you feel. Why it is? You can see that this is a borderline. But it is no critically, apparently line drawing is no. Then only this is brightness, one brightness, second brightness, third brightness, like this. But you can see this is some line is the border. So therefore, it looks like some edge is more emphasized like this, maybe. Fine, it is. And also, this is a black square, black square, black square, and white corridor, white corridor, white corridor. But you can see some little bit, some dark circular is shown here. Fine, it is. This is called Harman split. This is called Maha band. This is both two famous optical illusion. Why it happens? Because of the lateral inhibition. Lateral inhibition, ne? What is the lateral inhibition mechanism? これはハーマンっていう人とマッハっていう人は、これはオーストリアで、この人はジャーマニーの人で、19th century, late 19th century and the early 20th century's psychologist ですけど、でそれは、これは、lateral inhibition のメカニズムは、the cleared by the Haushofer club の、このレティナで分かったんだけど、because one layer is here, and one layer is here, one layer's sensitivity nerve cell is here, and in this case, yes, this bright light is given here, and no light given here, in this case. So the A part's center nerve produce this amount of brightness stimulus output signal. This amount of output signal is produced becauseこのbright light received cell is produce some amount of output signal, but the neighboring cell is give some reducing signal from the other neighboring cells. Some reducing signals. Inhibition signal is given from the neighbors. So all the neighboring cell give some reducing signal. So therefore, in total, the output signal looks like this. But the B part, some part of cell is a black part, non-bright part. So therefore, these cells is not producing the reducing signal. So the inhibition signal is only limited cells, given from the only limited cells. So therefore, the output signal is become higher than the A part. For the C part, this is the border. This is a dark part. But the neighboring cell is a bright part. So therefore, their cells is produce some inhibition signals. So therefore, the C part of cell produce more darker signal. More darker, more reduced signal output. And D signal is the non-condition. So this amount of brightness output is produced right here. So therefore, the border part, this border's bright part is produce the more brighter signal, brighter output, and the darker part at the border is produce more darker signal. Okay, so this is the mechanism of the inhibition, neighboring inhibition system. Then this is a comparison between visual sense, auditory sense, and tactile sense. It looks like this. This table is skipped. And finally, the skin sensation. In the skin, there are some sensory organs is inside of the skin. Some MR とか MK とか R とか P とか、こっちも the hairs sensation とか、なんか F とか PN とか MR とかいろんな、なんかこういう名前のtactile sensation とか pressure sensation とか temperature sensation とか pain sensation とか Yeah, this is looks like this. This is 1, 2, 3, 4, 5, 6, 7 とか 7 kinds of the sensory organ is there inside of the skin, and each of them is for example, this is a temperature, and this is some amount of vibration. This is lower frequency vibration. This is acceleration. This is pressure force, and so on. So therefore, each of them has some special features about adaptation, and the receptive field looks like this. And totally, this is when some the frequency is given to the stimuli, and given to the skin. Some this is a threshold of the which kind of amplitude can be distinguished is here. So this is physically, psychologically it looks like this. Each of the sensory organ is looks like this. This is これは physically、これは psychological sensation で、これはパチーニっていうパチーニ素子、パチーニ element。And this is a skin surface sensation. And totally, we feel this black dot line looks like this. So therefore, for the vibration stimuli, we can feel sensitively about the 200 several 10. 220から220, 230 is the most sensitive about the skin sensation, about vibration. This is used, this vibration frequency is used for the tactile feedback systems, devices. で、これが面白いのは、finally, this is an interesting feature. The Sidney Weinstein, 1968, he has made two very famous charts. One is 2-point discrimination threshold. Yes, the needle stimuli is given to the palm or the forearm or every part of the body, and the smaller is better discrimination. To distance or two needle distance. So therefore, the hand finger part is more sensitive. But about this stomach or lower limb part is not so sensitive. Yeah, you can see. And also this is localization. Yes, when the stimuli is given without visual information, this patient, this subject can recognize the real location correctly or not. This is error is given here. So when the error is small, he can estimate the location more exactly. So therefore, of course, the hand part and also the face part and the foot thumb is a little bit sensitive about the localization. Looks like this. これ、ローカライゼーションはどうやってやるんですかって言ったらこうやるような今テスト。
This next test, I'm going to take this caliper and I'm going to touch 1 point or 2 points. And I want you to close your eyes and tell me whether I'm touching with 1 or 2. 1, 2, 1. Good. 2. Good. Now you get up on the palm. 1 or 2. 1, 2, 2, 1. And we test over here. 1 or 2. 1. Good. 2.
とかやってますね。OK。というわけでこういうテストをしながらどこが which part is sensitive, which part is dull. It can test it So therefore, the around the facial and the finger, chest, and the abdomen is sensitive, but the arm or leg peripheral part is the blue. Okay. というような感じで今日はおしまいなんですけど、あとはなんかこの例えばタクタイルセンセーションはドットドットドットだけど maybe it can feel like the line ドットドットドットだけど it can feel line とかファントムセンセーションとかマスキングとかも also at the skin sensation we feel like this and thenこれは little bit old data but the handicapped person is so many in Japan. So therefore, some the supporting devices is developed, and also now for the physical handicapped about the visual impaired or the auditory impaired or something is so visual impaired, hearing impaired, and vocally impaired, and physically disabled is also there. So therefore, some supporting devices we will discuss next week. Okay? で、これはlast week some student is going to the fair exhibition at the Kokura, but this week some also the similar manufacturing fair is held at the Fukuoka, Hakata. So therefore, if you have some time, you should visit that manufacturing fair. Look at this, if you have some chance. But it's also the weekday, only Wednesday from tomorrow to the Friday, Wednesday, Thursday, Friday. Some exhibition is a manufacturing exhibition or next generation technology exhibition, and also some special event. The ET Robo contest exhibition match is there, using the Lego Mindstone system. So therefore, if you are interested, you should attend there.